Hello, today we're going to talk about reactivity 3.4.4 and 3.4.5, and this is all about electrophiles and electrophilic addition reactions of the alkenes. So let's talk about electrophiles. They were briefly introduced in an earlier section, but electrophiles can accept electron pairs when you are forming coordinate bonds. And remember, a coordinate covalent bond is when one of the two elements in the bond is providing both of the electrons, which is different than a typical covalent bond where each bonding atom is providing one of the two electrons. So an electrophile is something that accepts electron pairs. Think about it this way: an electrophile, electro is for the electrons, or the negatively charged electrons, and the suffix there, phile, means it's attracted to. So it is attracted to the electrons, it accepts electron pairs. Now electrophiles can be neutral, or they can be cations. There we go. And some examples of neutral electrophiles include like hydrogen halides, halides themselves. Water could act as an electrophile. And there are a few other things, but those are some common examples. They could also be positively charged ions, so things like NO2+, hydrogen ions, other like transition metal ions could be the cations involved. Now let's get into a type of reaction called an electrophilic addition reaction. And this is always going to involve an alkene plus an electrophile. And the reason that this works is when you have an alkene, you have a double bond between two carbons. And remember, when you have double or triple bonds, one of those bonds is a sigma bond and the other one is considered a pi bond. So that pi bonding has a larger electron density, so there's more electrons, and those additional electrons can attract electrophiles to them. So whatever your substance is, it's going to break that pi bond, split it up, and you will wind up with an alkane, a single bond between the two carbons, like this. And there are a couple different options that we're going to look at today, but a really common one, like this is a version of this, is hydrogenation. Although we will typically think about hydrogenation as a reduction reaction instead of an electrophilic addition. But you could add H2 and have hydrogens on both carbons. It's just more likely to be talked about as a reduction reaction than an electrophilic addition. Now, one of the things that could happen is you could be adding water. So you have your alkene, and you need to be adding a water molecule. And what happens is that the water will split into hydrogen and hydroxide. So this works really well when you have acidic conditions, and you will see that pop up. But then the double bond breaks, and one of the hydrogens attaches to one of the carbon, and the hydroxide attaches to the other. So another name for this is called hydration, because you're adding water, but you are adding hydrogen to one side and hydroxide to the other side, creating a new alcohol from the alkene. You could also have an addition of halogens, which is a type of halogenation, where you take that alkene reaction and you're adding in some halogen like this, and you are again breaking the double bond, and one of each of the halogens will go on each of the carbons. So you will create a dihalogen alkane as a product, like a dibromoalkane or a dichloroalkane. One thing to notice with this is that if you use bromine as your alkane, as your halogen, Bromine is a like brownish orange liquid. I'm just going to write brown for simplicity. But if you have an alkene and you put in bromine water, which is brown, it will turn into a colorless product. So you can confirm that the reaction did happen based on that color change. Now the last type of reaction here is going to be the addition of hydrogen halides. So we've got our alkene and our hydrogen halide, and again the double bond will split like this, and hydrogen will add to one side, the halogen will add to the other side. Now typically then it will form just a halogenoalkene instead of a dihalogenoalkene, so a single halogen added. One thing to note is that HI is more reactive than HBr, which is more reactive than HCl, in that order. The bond between the H and the I is easier to break. So it's easier for this to split apart and then go in and split apart the double bond for the alkene. So if you notice that general trend for reactivity, these one will react more than the HI will react more than the HBr or the HCl. Okay, so here's an example. We have condensed formulas and names of the products for the following reaction. Our but-2-ene. So I have CH3, with a double bond, CH3. That's but-2-ene. It's reacting with HBr. It will form CH3, CHBr, CH with another H, and CH3, like this. So I can condense that further, CH3, CHBr, CH2, CH3, and that would be 2-bromo-butane for that reaction. So for this one, explaining how bromine water can be used to distinguish between an alkane and an alkene. They both can react with bromine, but for a reaction of an alkane, if you go back to reactivity 3.3, it has to have UV light to catalyze the homolytic fission and get the reaction started. For alkenes, it can happen in the dark. So if you add bromine water in dark conditions to both of those things, the alkene will react and change to a colorless solution, whereas the alkane will not. So this goes right back to that previous example. Why is it decolorized in the dark by alkenes? Because you do not have homolytic fission required for an alkene addition. But for the bromine to react with alkanes, it has to have UV radiation to split it into the bromine radicals, which then can react with the alkenes. Now this also links to structure 2.4. Why are alkenes sometimes known as starting molecules in industry? And that's because you can split that double bond and add a whole bunch of different things to it. You could add in hydroxides, hydrogens, or halogens to a specific point in the molecule based on where the double bond is located. So it helps us to make products that we're looking for by starting with the proper alkene.